All right, hello, this is Jeff Scott of Blackhawk Technical College. I know that some of you who are in the 152, 143 Introduction to Java Programming class have not yet had me as an instructor. If you are not aware of this, I tape all of the lectures that I give in the classroom. In addition, for a class like 152, 143 Intro to Java Programming, I'm going to make extra tapes. We're going to go over the first 9 or 10 chapters of this 18-chapter book in the spring 2016 semester. And so what I'll do for each chapter is I will do one lecture, and I'm doing this from home, where I go over the PowerPoints, go over another lecture where I go through the stuff that's in the book, and then we'll have our lectures in the classroom also. What that'll allow me to do is when we're in the classroom, what we will do is just simply work on programs as a class. So, Chapter 1, start right at the beginning. Now, some of the stuff that's in here, for instance, I'm not going to go over hardware and software. Why program? Well, I mean, one reason, I guess, is because hopefully you'll get a job in the field. We'll talk a little bit about the programming languages, and about 4 or 5 of the ones that are mentioned in there are ones that are taught in the program here. We will talk a little bit about what a program is made of, the programming process, and then a brief introduction to object-oriented programming. All right. Java, as you can see now, is close to 25 years old. It was originally called Oak, and the reason supposedly is because James Gosling, who is one of the originators of the language, had this huge oak tree outside of his office window that he looked at all the time as he was creating the language, and decided to call the language Oak. So why is it Java? Well, evidently when they tried to put a patent or whatever you have to do for naming a programming language, they found out there already was a language named Oak. So they changed it. And rumor has it, because this has never been confirmed one way or the other, that Gosling and a bunch of his friends were sitting around a cafe drinking their coffee, and that's when the idea hit them to, let's call this Java. All right, so again, about 20 to 25 years old. It's cross-platform. The idea is you can run Java on various computer operating systems. Not only that, other than possibly a recompile as you go from one platform to the other, the programs should basically work with little to typically no changes other than the compilation to have to take place. What we will do all of the spring 2016 semester is we will do Java applications. As it says, applications are standalone programs. So for instance, if we were to make a payroll system, we could make it in Java or something like that. All right. During the fall semester, one chapter in the book, and it's about chapter 14 or 15, something like that, is on Java applets. Applets are small programs that are designed to run inside of a web browser. All right, so again, why program? We've already talked about it, all right? Hopefully to get a job and a few other things, okay? So these are things that you're going to have to worry about. Now, everyone who's in this class should either have had the 152, 119 Learning to Program with JavaScript class with me, Jeff Scott, or with Jim Schmidt. So ideally, you've been introduced to the logical flow of instructions, mathematical procedures, the appearance of screens, etc. All right, at least somewhat. And we'll go into it in more depth and breadth of coverage this semester. I will tell you that if you're taking all the classes in the program, you'll be taking 152, 143 Intro to Java Programming with me, and 152, 142 Intro to .NET Programming with Denny Wright. Denny will probably have you up and doing GUI stuff, graphical user interface stuff, almost right away, maybe within the first week. In here, we're going to do a little bit of GUI stuff in Chapter 1, but the majority of the actual GUI stuff that we do in here, we won't do until the fall semester. All right. So, as it says, programs must be analytically correct. They rarely work the first time as they're programmed. Another thing about that, and we'll talk about this later on in the chapter here, but again, in an ideal world, if you're given a set of computer program requirements, rather than just sitting down and starting to type in and using the first idea that comes to your head, you're much better off to sit down and think about it for a while. Think of a few different ways of solving the problem. Sometimes what happens is the requirements are supposed to drive your program. But sometimes you start writing a program and the program ends up driving the requirements, and that's not the way it's supposed to go. All right? So you should analyze, experiment, correct, and redesign as necessary. Programming languages have strict rules. The rules of the language are known as syntax. For instance, in any executable line of code in a Java program must end with a semicolon. You go, oh, just like JavaScript. Well, in JavaScript, if you left the semicolon off where one was required 9 times out of 10, really 99 times out of 100, the program would still work fine. Not in Java. You'll get a syntax error then. So, computers consist of hardware and software. Hardware consists of a CPU, all right, central processing unit, which consists of an arithmetic logic unit and a control unit. You've got main memory, which is the RAM of the computer. You've got secondary storage devices like a hard drive. You've got input devices like a mouse or a keyboard, and output devices like a screen or a printer. Okay? And I probably have hit on a lot of this stuff already here. So there's the central processing unit. Again, it does all the arithmetic and logic operations, and it kind of is the conductor, so to speak, of what goes on in the system, and that's the control unit part. It performs, as it says here, a series of fetch, decode, and execute in order to process a program. All right, I don't want to read to you so you can see all that stuff. I'll leave that up there for a second. Main memory, again, RAM, we've already talked about it. And RAM is volatile. In other words, it is subject to electronic current. Now, that used to mean that you had to have your computer plugged in, but now with the sophistication of batteries and stuff on the computer, what that means is there has to be power going to the computer in order for the stuff to be in RAM. Once the power subsides, whatever is in RAM will be removed. They get into talking about bytes and addresses and stuff, and really addresses are important. And one thing to remember, and some of you have heard me give this analogy before, that if for some reason Blackhawk Technical College were to move out of their current location tomorrow, the address of that location would still remain 6004 South County Road G. They could have different occupants, but the actual address wouldn't change. And the reason I'm telling you that is in much the same way. Computers, in their memory, they have addresses, and those addresses don't change. Over time, what those addresses have or will either have directly inside of them or what they point to, that may change, but the addresses themselves do not change. I always love that when you see stuff like this and you see pictures of memory and someone will say, it doesn't look like that. Well, memory basically is an abstract thing, so the author is trying to draw, an abstract diagram of what it may kind of resemble. All right, secondary storage, again, disk drives, CD drives, DVD drives, USBs, etc. Those are non-volatile, so they're designed to hold information that you want to keep after power has been, gone from the computer. Input collects data. Input devices, keyboard, mouse, scanner, digital camera. Output sends it back to the outside world, monitors, printers, etc. Really, the whole act, before it was called computer information systems or information technology, this was known as data processing. And data processing meant that you took data, you inputted it into a computer, you processed that data, and you outputted information. So really, data processing was the conversion from data into information. And the difference between those is data may or may not make sense depending upon who is looking at the data. Information must make sense to anyone who views the data, or the information, I should say. All right, there's 2 classifications of software. In this class, in this program, we're concerned totally with application software. If you want to know more about operating systems, you should take a class or whatever in the Network Specialist program. All right. An operating system manages the computer's hardware devices and controls their processing. All right. And a little bit more. You can read that on your own if you have an interest, okay? Application software, again, the type of software we're going to create in here, refers to programs that make the computer useful to the user. Many of the programs that we write, especially when we first start in here, are going to seem very simplistic. All right. For instance, in maybe chapter 2, we'll do a program where you put in how many miles you drove and how many gallons you used, and it'll tell you your miles per gallon. And then we're able to go and add onto that program to make sure that the user puts in numbers, to make sure that the numbers the user puts in are are positive, etc. So a program is a set of instructions the computer follows. These instructions collectively are known as an algorithm. An algorithm, the idea is, an algorithm is like a recipe. And if you follow the steps, so if you write a program and anyone runs that program, they should given the same inputs, they should get the same outputs. You know, and it's funny because I've heard this for years where people compare an algorithm to a recipe. The thing is, I always remember my late grandmother. She could make things, and my mom could use the same recipe and make things as my grandmother, and they would taste totally different. All right? So the computer needs an algorithm, and eventually all that code that you put in there has to break down into what's called machine language. Machine language is a series of binary or base 2 0 and 1s, because that's all the computer in the end can understand. In the past, programmers wrote programs in machine language. I will tell you that I got my first data processing degree. It must have been in the, I don't know, maybe the early 80s. And the year that I got my degree, which was like, I think about 82, must have been around 80 in the school that I got my degree from. That's the first year they stopped making students at least write one program in machine language. All right. But I did write with assembler. And assembler is about as close as you can get to actual machine language. Some of the common programming languages are shown here. If you go down column by column, in the first column, we teach Java. Of course, that's the class you're in now. In the second column, we teach C and C# and PHP. In the third column, we teach JavaScript. All right, so you do have an exposure to several of these top languages that are mentioned in the slide here. All computer programming languages have things in common. They all have keywords, although the words can differ between languages. They all have operators. Typically, they all have addition, subtraction, multiplication, division, etc. They all have punctuation. All right. In some languages, every time you've got a series of lines of code, you have to put them between the words begin and end. Other times, you have to go and put them in between curly braces. All right. Java, for example, as we already mentioned, with punctuation, every line of executable Java code must end with a semicolon. They all have programmer-defined identifiers. Those are the names of variables and other things that you create, functions or methods or classes, etc. Here's an example of a Java program. I'm going to leave it up there for a minute and we'll take a look at it line by line. So breaking it down from the top, and I know they do this later, but I just want to do it myself here. You'll notice the first thing it says here is public. This is called an access identifier. Since it's public, literally its domain is the world. So in other words, anyone can use this class because the class is public or available to everyone. All right, it's public, it is a class, and its name is Hello World. Now, two things about this. First of all, Java is a case-sensitive language. Public must be spelled correctly, and it must be all in lowercase. Class must be spelled correctly, and it must be all in lowercase. Hello World, that's one of those programmer-defined identifiers. All right? And the way that it's set up in this language is if you've got multiple words like we have here with Hello World, you always have the first letter of the first word and the first letter of every word that follows be capitalized, and everything else is lowercase. All right? And this is the syntax that I will expect you to follow when you're creating class names. So, we've got a public class that's named Hello World. The other thing about this is whatever you put after the word class, you must save the Java program now as Hello World. And the case this must be the same. So again, capital H, lowercase ELLO, capital W, lowercase ORLD .java. Every Java application must have a main method, and that's what you see. I should mention too, Java is a block structure language. Each block is delimited by these curly braces like you see here and here. All right, so we've got main. Main is the name of a method. It too is public, which means it can be called from the outside world. It's static. For now, just look at static as being there's only one of them. So static in our case for what we're looking at now implies one. All right. Okay. Void means it does not return anything. Later we'll change that. We'll change it to different data types so we can return something. Main is the name of the method. Every Java application must have a main method. All right. It is possible for us to pass information into main. If we do, each thing that we pass in is part of a string array that's named args. All right. Arg short for arguments. All right. Unlike JavaScript, Java is what's called JavaScript is a loosely typed language. Java is a strongly typed language. So we can't just say var message equal hello world like we could in JavaScript. We have to let the system know it's a string. Also, unlike JavaScript, where we could have used single or double quotes here, when you have a string in Java, it must be in double quotes. So this is creating a brand new variable that's called message, and it holds the value hello world. This next line says what we want to do is print out on the console, all right, this message. So if we run this, it should print out hello world. Now, I'm going to break off from this a little bit. I wasn't going to do this. I didn't know if I wanted to or not, but I decided what the heck I would. So I'm going to copy this. There's the program right there. Okay, I'm just going to literally So I'm going to copy all of this, and just to show you, to prove to you, for lack of better words, what this is going to look like, I'm going to go out onto the virtual desktop here. I'm not going to explain right now how we set the virtual desktop up, how we do all this and that. I'm not going to do that. But what I am going to do is I'm going to just grab that code that you just saw. I'm going to start up Eclipse. Again, all of this stuff will be explained in the classroom, the stuff I'm going through right now. But I want to show you just exactly, if we grab all that information from that original file and we save it as helloworld.java and run it, what it will look like. So I'm going to come in here, I'm going to do a file, new, Java project. I'm going to, whoops, I don't know why that's there, but I'm going to type in hello world here. All right, I'm going to click finish. Again, all this stuff will be explained in class, so don't worry if it doesn't make a lot of sense right now. So there's right now there's not a lot in it, as you can see. Public class, hello world. All right. I'm literally just going to copy in everything I had in there before. All right. Public class, hello world, everything that you just saw. So now I'm going to save it, and I'm going to do run, and notice what appears down here. You say nothing. Yes, it's right there. Hello world. All right. So that's all we did was we told the system to literally print hello world to the screen. And as you could see, it worked just fine. All right. Now, as you'd guess, the programs will get a lot more complex than that, but just so you had a little bit of an introduction. So again, the keywords in there were public, class, static, and void. Java is case sensitive, so all keywords are in lowercase. We're going to go over the majority of the keywords as we go on in the semester. Some of the keywords we'll never talk about, and some of the keywords Java actually created so you couldn't create them. For instance, in the Java programming language, goto is a keyword. They never want you to use it, period. So they made it a keyword so that you couldn't use it. All right, you cannot create your own variables that have the same name as a keyword. In other words, I couldn't create a variable named public or void or static or class. We already talked about the semicolon. We'll see when we go over the book part. There's a few places where you don't need to put a semicolon in. We'll talk about those. All right. It says there are differences between lines and statements when discussing source code. All right. And it says this is one Java statement that was written using 2 lines. All right. So you can break it up over 2 lines like this. The only time that you cannot break a statement up over 2 lines, so going back to the program that we just looked at, the one I just created and ran for you right here, we could have said, for instance, where we got the hello world, we could have put that on a different line. There's not a problem with that. Save it, run. There it is, hello world again. What you can't do is you can't take a string like we have right here, and you can't break this string up over 2 lines. All right. Notice when we did that, the editor put in plus world for us. But if we remove this, we remove that plus sign and do that, we get an error message because we're attempting to put the string over 2 lines and the system doesn't understand what we're trying to do. All right. And when the system doesn't understand it, you know, it's the fight between you and the software. The software is going to win. That's just how it works. All right, what's a variable? A variable is a named memory location. Actually, it's a value at a named memory location whose value may vary. All right, here's an example of a variable. Int hours equal 40. Remember, this is a strongly typed language. The word var goes away in this language. Since this is going to be a whole number with a value of 40, all right, we say int, meaning it's a whole number that can't have a decimal place. There are actually 2 things going on right here. And I want you to understand that, again, that there are 2 things going on. All right, really 2 things are happening here. The first thing is we're doing this, int hours. And to say int hours, that's what's called a variable declaration. All right, but we could have broken it up into 2 lines like this and then said hours equal 40. That is a variable initialization. All right, so why am I taking the time to show you this? Well, I am just because of the fact that you can do it like that and break it up over 2 lines, or you can combine them into 1 line. So you're doing both the declaration and the initialization on the same line, which again is totally legitimate to do. All right, probably more often than not as you get going in here, you'll do it that way where you put them both on the same line as shown right here. All right, as it says, variables are simply a name to represent a place in memory, and that's what they are. Now, just so you know too, it doesn't actually look like this in memory. It's not 72 because, again, remember, all the computer can understand, all right, the only thing that the computer can understand are zeros and ones. So if we wrote that in binary, if we wrote the number 72 like that in binary, it would be what? I'm going to have to do this backwards. 1, 2, 4, 8, 16, 32, 64, if I did my math right. So what? 1, 2, 4, 8. 16, 32, 64. So 64 plus 8, all right, 64 plus 8 would be 72. So that's how that number, that 72 that you see right there, that's how it would be put in memory. Because again, all the computer can understand are zeros and ones. Now they talk about the Java virtual machine here. It says how it actually decides where the value will be placed in memory. And again, I have no idea if Denny will get into what I'm about to say, and if he does, how much. But in .NET land, they use something that's called the CLR, or the Common Language Runtime. And it's basically the way that the system works, gets your program set up, and you're able to compile and run your program. In Java, it's called the Java Virtual Machine, or the JVM, but it does pretty much the same thing. All right, so as it says, the programmer writes the program in source code. They use a text editor. We're going to use Eclipse in here. Source code files must have a .java extension. Now, with most programming languages that both compile and interpret, all right, with most programming languages that do both compilation and interpretation, most languages, they do the interpretation first, all right, then they do the compilation. That's what JavaScript does. If you remember with JavaScript, when you started to type something in and you made a mistake typing or whatever, sometimes, depending on the editor you're using, you might have even gotten an error message right away. That's the interpreter part. All right. What a compiler does is it goes through your entire program, flags errors, but it keeps going. So an interpreter stops when it finds a mistake. A compiler keeps going, but it flags the error. Imagine it this way. Let's suppose I'm talking with a person on the street, and the person that I'm talking to is Spanish, and I'm English, and I don't know any Spanish, and they don't know any English. So we bring in an interpreter. So I say something in English, and they start to interpret it immediately into Spanish, but I come up with a word, whatever the word is, and they don't know the Spanish equivalent. So they stop for a minute. And they have to go look up the word as far as what the word is in Spanish. That's interpreting. On the other hand, if I go and I talk for a minute or two, and the person basically writes everything down, and then when I get done, spits everything back at the person from Spain, they're doing more a compilation. All right. So again, most programming languages are like JavaScript. They interpret, then they compile. Java compiles, and it compiles into what's called bytecode, and then it interprets based off of that. When the compiler is running, it might find syntax errors. What do I mean? Well, notice that. Remember that program that we just looked at? All right. I'm going to remove that semicolon. All right. Now, I'm going to save, and I'm going to attempt to run the program. And I get errors exist in the program. Do you want to proceed anyway? Virtually all the time when that happens, you want to tell it to cancel. You can see I've got a red X there. And it says syntax error. Insert a semicolon to complete the statement. All right. So I put the semicolon, boom. Now I have not broken any of the rules. So now everything is okay. I save. Notice that my error went away over here. How about this? What if I come in here, instead of void, I write VOYD for void? I get a different error because the system doesn't know what I'm talking about. It says void VOYD cannot be resolved to a type. It doesn't understand what that is. All right. Any of this stuff that's in here. String, if I accidentally make that sting instead of string, same kind of thing. But now it says, what do you want to do? Create a new class called sting, or change it, create the interface, etc. All right. Now what I want to do is I want to change that back to string, so I get rid of my error. Believe me, you'll have plenty of chances to make plenty of errors during the semester. We all do. So syntax errors are rules. You broke the rules of the language. All right. Again, most compilers translate source code into an executable that's called machine code. Java does not do that. The Java compiler translates your source code into bytecode. And then the bytecode As it says, that's the virtual language of the JVM, or the Java Virtual Machine. It ends with a .class file. So when I created that program before, and I did that hello world.java, and I compiled it, in the background it created a file for me called hello world.class. All right? The Java Virtual Machine is our interpreter, and that's why Java is sometimes referred to as an interpreted language. So here's the process. All right? So we key information in our case, will be through Eclipse. That's our text editor. We'll save our Java statements for example, as hello world.java. We go to compile it, so the Java compiler looks at it. If it doesn't have any errors, if it finds no errors, it'll create hello world.class. That's the bytecode version of our file. That is sent over to the Java Virtual Machine, or the JVM, and that results in, that interprets it, and it gives us our executable file. I mentioned before that Java is a portable programming language, which means that you can write it on one type of computer and run it on another. You probably have to recompile it, but typically you'll have to do nothing else. Notice that there's Java Virtual Machines for Windows, Mac, Linux, Starnix, etc. Java provides a different Java Virtual Machine for each platform, so the programmers do not have to recompile for different platforms. That may or may not be true. Again, there's one for Windows, for Linux, for Mac, for different types of Unix, etc. They go through a little history here, and you can read all that stuff yourselves as you've got an interest. I will tell you that a place you might want to look up, and this isn't the actual right address, but it's the old one. If you don't know, Java used to be owned by Sun Microsystems, but several years ago, Java was purchased by Oracle. But if you go out to java.sun.com, it pushes you out to oracle.com/technetwork/java/index.html. This is the home page for Java. And we'll go through it as we go on. That's Duke, and Duke is the Java mascot. All right. And Java is free. You can go out to java.oracle.com and download it on your own machine. You shouldn't have to, because it's already existing on the virtual machine. We have at Blackhawk in the virtual machine that you can copy for your own machine at home. Don't worry about any of this stuff where they talk about compiling a program. We're not doing it this way. We're doing it through Eclipse. So all this stuff that's in here, this is from a command line. So we don't have to do any of that. All right. The next thing that the author discusses in here is they go through, a 9-step process for how to program. What's interesting is, notice he's got the first 4 steps on this page and the last 5 steps on this page. You may or may not realize it, but when you look at these first 4 steps on the page here, clearly define what the program is to do. In other words, know your requirements. Visualize the program running on the computer, so maybe sketch it out on a piece of paper. Use design tools to create a model of the program. Could be a flowchart, pseudocode, or whatever. Check the model for logical errors. None of those steps necessarily involve the use of the computer. You can do steps 1, 2, 3, and 4 without using the computer. It's only when you get to step 5 that you enter the code into the computer and compile it. After that, it's correcting errors you find and repeating steps 5 and 6 until you get to the point where you have no errors. You run the program with test data, and based on that, you correct any errors you find. So really, steps 5 through 8, really 5 through 9 are things that can happen continuously as you're working on a program. All right, they mentioned the idea of software engineering here. You can see the different components, the different things that are involved. Software engineers develop program specs. Does this look familiar? All right. Know what your program is going to do. Kind of imagine what it's going to look like on the screen. All right. Develop a diagram of what it should look like. write some pseudocode or whatever. So all this stuff, again, does not involve necessarily the use of a computer. All right? All right, and the last thing that they discuss in the last few slides here in the chapter are procedural programming versus object-oriented programming. Older programming languages like C, etc., are procedural. With procedural programming, as it says, a procedure is a set of programming language statements that together form a specific task. In most non-object-oriented programming languages, these are known as functions. As it says, procedures typically operate on data items that are separate from the procedures themselves. All right? And you pass these data items from one procedure to another, typically. All right? And there it's shown. In procedural programming, as mentioned here, procedures are developed to operate on a program's data. The data tends to be more global to the program. Now, with object-oriented programming, the idea is you have an object, and an object holds the data and the procedures that manipulate the data. They're all held inside of the same unit. The data are typically known as attributes. The procedures are typically known as methods. Now, he gives you this picture in here. You can look at that and read that on your own as well. A couple of definitions and terms in here. Object-oriented programming combines data and behavior via encapsulation. So you don't really, as a user, have to be even that aware that the data and the behavior are put together in a unit. You just have to be able to use them correctly. And really what encapsulation involves is this next term here, that's data hiding. It's the ability of an object to hide data from other objects in the program. All right? Only an object's methods should be able to directly manipulate its attributes. What the heck does that mean? That means, in a nutshell, and what I'm telling you now is a gross overstatement, and it's not always true, but it's mostly true. What object-oriented programming is about is it's using public methods to manipulate private data. And that's what they're talking about. All right? And that's it for this first chapter. So again, I'm going to do the first 9 or so chapters, and I'm going to do all of the different lectures for the PowerPoints, and I'm going to come back and do the book. Okay?